All right, so let's start this off with a little bit of a story. The story takes place at Balboa Park. I'm sure, I hope most of you guys have already been to Balboa Park at some point in your life. But what you may not be aware of is that there's actually a secret Balboa Park that you probably haven't been to. So Balboa Park is where the San Diego Zoo is at. There's some museums down there and all those kind of things. But there's an actual park called Balboa Park that you have to walk across this really big bridge to get to, and it's actually like really far outside of the area that's called Balboa Park by most people. But at this park, Balboa Park, there's a little playground area that has this big plastic like saucer shaped thing where kids can sit and you can spin it. So I've got it kind of like sketched roughly in front of you. So kids sit in it, and then people from outside can spin it as fast as they want. And what's fun about it, and the reason why kids enjoy it, is as you spin it, their bodies want to go in straight lines, which means they feel like they're being pushed backwards. They're really not. They're really being thrown in straight or pushed in straight lines. But as the object itself turns, it gives the feeling, the impression that they're being pushed backwards. But we've talked about that with centripetal motion in the past. So when they're sitting in there, you can spin them, and the faster you spin it, the more pushed to the back that they get, and the dizzier and dizzier that they feel. When I went to Balboa Park a couple years ago, I think my 10-year-old must have been like maybe 6 or 7 at the time. Went there with his cousin, loaded them on there, started spinning them. They were having a great time. And as usually happens when there's one fun adult at the playground and the rest of their lame parents, uh, as I was playing with my kids, more and more kids wanted to participate. So more and more kids started piling on or asking me to stop it so that they could get on. And I was like, yeah, you know what? No big deal. Definitely, it started getting harder and harder though to get it moving because as there were more kids on there, there was more mass around the outside, so the rotational inertia increased, and I had to spin it, push it harder, apply greater torque in order to get it moving. Of course, as a giant science nerd, all of these things were going through my head as I was doing it. So as I'm spinning it and as they're having fun, it occurs to me, you know what? I can mess with them a little bit. So I told all the kids who could to lean forward. So the kids who were paying attention to the weird grown up all leaned forward, and something really exciting and fun for me happened. Because when they started doing that, all of a sudden, without me doing anything, the entire the entire apparatus sped way up, like really fast up. Like they all leaned forward, and all of a sudden it started going fast. That almost all of them got thrown right backwards again. But then, as soon as they got thrown backwards again, uh, they the merry-go-round or whatever you want to call it slowed down again. So understanding what was happening here, I yelled, "What are you doing? Lean forward, like I told you to." So they leaned forward. All of a sudden, it sped up again. Meanwhile, the kids who weren't leaning forward were having like this insane ride because while they were back and it sped up, all of a sudden they were getting really dizzy. So I was able to get them to do it 2 or 3 times before like basically their abs couldn't handle the like leaning into towards the center, fighting against that that apparent force that was pushing them outwards. Yeah, so there's the story of me messing with kids at the playground. That I regret saying that in the video. Don't share that with anybody. So let's talk about angular momentum and let's talk about what was actually happening. So the formula for angular momentum is L equals I omega. L is the variable for angular momentum. And the units of angular momentum are kilogram meters squared per second, which is pretty similar to the units of linear angular momentum, kilogram meters per second. There's just an extra meter in here that I think I talk about in a later video. The two other variables, there is the rotational inertia, and there is the angular velocity. So this is a pretty simple formula. It only has two parts, nothing squared. There's no weird like half coefficients or fractions or whatever. But and probably if we're doing angular momentum, you won't see a ton of stuff that only talks about like the angular momentum of a single system. At worst, what you might see is you might see some kind of graph that says angular momentum versus angular velocity, and the slope of this would have to be the rotational inertia. But probably that's not even going to come up in a problem, because the thing that they really care about with angular momentum is they care about conservation of angular momentum. Conservation. And conservation of angular momentum works like all of our other conservation rules. That basically says unless there's something outside the system acting on it, the angular momentum always has to be the same. In this case, the thing that we don't want is we want no outside torque. So conservation of angular momentum did not apply when I was pushing this ride in circles. Every time that I gave it a push to make it go faster and faster, we couldn't apply conservation of angular momentum because I was an outside torque on that system. Conservation of angular momentum did apply, but unfortunately, since I was part of a system that included like friction with the Earth, as I was spinning it, I was actually like slightly slowing down the rotation of the planet temporarily, but like by such a minute value that it's not even worth discussing. But once I kind of stood back and started saying like lean forward, lean back, lean forward, lean back, laughing my head off as these kids were like about to puke their guts out, um, then we can start talking about conservation of angular momentum. Because where it starts getting interesting and where the problems start coming up is basically the idea that the rotational or the angular momentum before, this is the initial value, should be equal to the rotational, the angular momentum after. So there's a couple different ways to write this. One of the ways that I've kind of seen it on some exams is they say, okay, the initial is IA, WA, and then we can say that there's like a coefficient A and a coefficient B that modifies these two values. But however you want to look at them, as those kids were spinning and as they leaned forward, let's talk about what was happening to their rotational inertia. As they leaned forward, we can imagine that they were like a long object that was spinning along this axis. And we were going from the mass being here to the mass being here. That is mass moving closer to the center of the axis of rotation. So as they were doing that, the rotational inertia was decreasing. So basically this A value decreased. But since the value has to be constant, we have conservation of angular momentum here. As the rotational inertia decreased, the angular velocity had to increase by an equal value. And so that meant that they were spinning faster as they leaned forward. Then when they leaned backwards again, the rotational inertia went back up. So the angular velocity went back down. And you can kind of repeat this over and over again. This shows up in a lot of different problems. The most classic one, and one that I'm sure will come up in class, is if we talk about ice skaters. When an ice skater starts the rotation with their arms out, they kind of like throw themselves in a circle. They already have a spin. They've set the angular momentum for their particular system by pushing off the ice and using friction to get themselves going with an applied torque. But then when they start pulling their arms inwards, they're decreasing their rotational inertia. And as their I value decreases, just like happened with these kids, their omega value increases and they start spinning faster and faster. So when you see those ice skaters spinning like super fast, and they're up and they're like straight up and down, their arms are up or their arms are down at their side or something like that. They've gotten to the point where their rotational inertia is very, very low, so their angular velocity gets really high. And then when they're ready to come out of that turn, they start flattening their body out, spreading their arms out, putting a leg out, all those kind of things, increasing their rotational inertia again, and lowering their angular velocity. So that's the big idea of angular momentum, is that by playing with our I value, we can change our omega value. And this is different than linear problems, In linear problems, where we had P equals mv, the conservation had more to do with collisions between objects than systems that were kind of self-contained, because it was really hard, or it's nearly impossible to like directly change a mass value to cause a change in the velocity value. But because rotational inertia is just about moving where the mass is within the system, and we're not trying to make mass appear out of nowhere, we can start having this exist within a single system without having collisions. You can still have collisions with angular momentum, where I could have like one spinning object come in contact and forcing another object to spin. And there too, we would have conservation of angular momentum. But the big one is some kind of like self-contained system that's happening. So there's what you need to know about angular momentum. Thank you guys for tuning in.